you can start it.
Okay, so I suppose I'll think I'll get about 40 to 45 minutes for the talk, and I think that will be followed by discussions.
That would be perfect. Yeah.
Okay, so you may, I mean, if I take a bit longer, please give me a caution because sometimes I might not keep track of the time.
All right.
Okay, so shall I start?
Yeah, please go ahead.
Yeah. Okay. Hello everyone. This is Munmun from Tezpur University, Assam, and I'll be talking about cosmic air showers and related detections and some of my research based on that. So at the beginning, I would like to thank the organizers for giving me this opportunity to present this work in this forum. So the outline, and then I'll talk about the we study or we need to study in extensive air showers, and then I'll be talking about one research work of mine on based on the study of a certain particle muons in the extensive air shower. So I start with the introduction to cosmic rays. Cosmic rays are particles coming into the Earth's atmosphere from any external sources. So we can call them as particle messengers from the sun, the Milky Way, other galaxies, exploding stars, and other happenings in the universe. Cosmic rays were discovered in 1912 by Victor Hess based on observations on mountains and in balloons. So what was seen there is the intensity of radiation increases with height from sea level. As we go up in the atmosphere, we see more and more radiation, which actually indicates outer space connection. Most of the cosmic rays, particularly the lower energy protons, come from sun, and very high energy radiation comes from outside of the solar system and even outside from some extragalactic sources which are placed beyond our galaxy. So actually, although the cosmic rays were discovered in 1912, actually there were some happenings which were going on for a long time. I mean, which were actually giving some indication of having some radiation in the atmosphere, and then it was started probing for the source of it. Coulomb electroscopes are some devices which were made to detect certain charges certain charges. So it's like it usually consists of a pair of thin plates uh, and attached to an electric conductor, so that like if it is in at the vicinity of something charged, then it can either attract or repel based on what kind of charges are developed on each of the thin plates. What was seen that even these electroscopes are very well shielded from radioactive sources and all. We expect that the electroscopes will like remain charged for a long time, but it was seen that actually they kept on discharging very quick, and it was guessed that it happens due to ionizing of air from charged particles. So it was like a very preliminary hint. Then in around in 1910, there was a very exciting experiment by Jesuit Wolf, who carried a few electroscopes to the top of the Eiffel Tower. So approximately about 330 meter above the ground, it was found that the radiation, the electroscopes detected about 60% higher discharge rates. I mean, detected more ionization as they go up. Okay. And it was seen that intensity of radiation.
Moon, your voice is breaking because of the connection, I guess. Can you hear me?
Yes, madam.
I think there are some connection issues. Let's wait for the speaker to join back.
Hello, can you hear me?
Yeah, now we can hear you.
Yeah, sorry, I just got disconnected. I mean, because of the weather, it's actually very drastic weather here.
I
So
see.
I'm just
Okay.
trying to. It's been raining very heavy. Okay, so but somehow I'm not being able to share my screen. So could you try to make me a co-host?
Oh, I see. Okay.
Or maybe that's the problem.
Yes. Santosh, are you there? Just wait a second.
Yeah, sure.
There is a technical issue. Please be patient. The speaker will join.
So I'm not being able to share the screen, but I have actually
Yeah, I have.
sent my PPT. So in
Yeah,
case
can you try now again?
oh yeah, now I can. Okay, can you see it?
Yeah, we can see. Thanks.
Okay. I have apologize for the inconvenience. So I think I actually I was talking this. I don't know how much you have heard. Like
Yeah, you can continue from here.
yeah. So basically, the interesting experiment was like carrying some electroscopes up high in altitude and also carrying another electroscope down below the sea level. It was found that as we go up in the atmosphere, the we find that the ionization or the radiation present amount of radiation present increases, and as we go down below the altitude we come near and near to the ground level, and even we go below the sea level we find that the radiation is decreasing. So it was some interesting hint about. So then in 1912, Victor Hess did some exciting experiments mounted on a balloon. He actually carried some particle detectors in a balloon and he went up. He ascended up to about 5 to 9 kilometer and found that average ionization increases with altitude. So you can see this plot, like the here this plot is about the ionization detected by two different detectors, chamber 1 and chamber 2, as a function of the altitude. And based on that, it is it's the ion pairs per volume per second was actually calculated and shown here in the second plot. You can see that how this ion pairs produced in the atmosphere based on that experiment goes up as altitude increases. And Millikan actually named them cosmic rays because he actually thought that these are photons only, these are lights only, and that's how the name um, was given as cosmic rays. It's slightly misnomer because cosmic rays it's actually cosmic particles. It can be different particles, but still the cosmic ray the name stays on. But we know that it's not only photon but other particles, other charged particles as well. The next period from 1932 to 1947 has been very exciting for particle physicists because using the cosmic ray information depending on experiments where cosmic rays were detected using various detectors, uh, s- like discovery of many particles happened, like discovery of positron. Then there were measurement of radiation intensity based on magnetic latitude, discovery of muon, and then discovery of extensive air showers, which I'm going to discuss in detail, discovery of kaons and pions, lots of particles happened. So it was exciting time, particularly for the particle physicists. And radiation detectors were involved, and the particles that the radiation detectors detected were coming from the cosmic rays. The role of cosmic rays in the astroparticle physics can be actually discussed like this. Part of the rise of the modern physics, early radiation detectors showed a dark current in absence of sources, which actually were due to cosmic rays. And until 1950s, cosmic ray research was very equivalent to experimental particle physics. However, now this area got broadened up. And one important thing is that energy of the highest and cosmic rays, the highest possible energy which were detected using cosmic rays so far, are much higher than the energy available with accelerators, say the CMS, the CERN, LHC, Large Hadron Collider, whatever energy they can achieve. The energy of the existing cosmic rays are much higher. So it's a natural particle accelerator, particle hub, where we have very highly energetic cosmic rays and we can detect them and we can understand their features. If we need to actually produce particles of that energy in our in our accelerators, the man-made accelerators, then it would actually, like, I mean, till now, I think about 10 to the power 14 or 15 electron volt is possible, but then we need much more sophisticated detectors. However, we have an abundance of cosmic rays already present in nature, which we can use for detection and further study purpose. The prospects in multi-messenger astronomy, which would actually connect the experimental astroparticle physics with astrophysics, is that you do combined study from different telescopes and cosmic ray detectors. So you can together you can do a combined study of certain events which would give electromagnetic radiation, gravitational waves, cosmic rays, neutrinos. I mean, from the same source these are coming, and we can use different detectors and telescope to different, like, find different components. So I mean, here I would like to mention about the event which occurred on September 22nd, 2017. So in the Ice Cube Neutrino Observatory, which is situated in South Pole, it's a huge, gigantic neutrino observatory, recorded a very high energy neutrino event. And at the same time, there have been some correlated detection of gamma rays in various telescopes. And finally, I mean, they were correlated with, the direction also, the reconstructed direction of the from the neutrino event as well as the detected gamma rays actually indicated that those the neutrino and gamma rays actually were produced from the same source, that is a blazar. It's so you see that, I mean, the correlated detection of different radiation coming from the same source blazar were detected. So it's exciting because now it's like a breeze between the experimental astroparticle physics and astrophysics, astronomy. Now I come to give an overview of the extensive air shower. Extensive air showers are like when any cosmic ray particle enters in our atmosphere, it will interact with the air nuclei, and instead of just one uh, particle, which we call as primary particle, entering and staying in the atmosphere, we actually have, as a result of the interaction, a large number of particles, like in a cascaded form. And these cascades, I mean, this we call as extensive air showers. Note that one extensive shower is actually produced by one primary cosmic ray, which is produced outside our atmosphere, and it just enters our atmosphere. So how it was detected was, like, actually there, I mean, the Pierre, Auger and Roland place, they placed some particle detectors in a modular array form. Initially, they had the detectors 20 meter apart. Later, they did this experiment to have more wider, to do in wider area. They also separated the detectors by 200 meter, but there are lots of detector stations. What was found that sometimes the cosmic ray particles or radiation were it was found that radiations actually arrive simultaneously within a small time window in all the detectors, or a large number of such detector areas, which can be called as coincident. They entered at the same time, and so that initiated an idea that this might be coming from the same event. So actually what exactly happens, I mean, in a graphical format, a pictorial format, we can see here that suppose this is a primary proton that is entering our atmosphere. It has entered, and maybe it will cross a small length, and then it will interact. As a result of the interaction, you can see that in different color, these are represented, like representing different particles, and you can see that it's actually a shower of particles, and slowly this shower would laterally expand, and finally it would reach the sea level. Some of the particles produced here will be unstable, and they will decay or interact very soon. For example, you can see this blue line, which is a pion, and it will decay to a muon, a particle muon, and also neutrinos. There can be some cascades of electrons, positrons, and gamma. And you can see that at the sea level, we get a huge amount of particles. So if we want to just see how this shower is developed, then at which altitude how many particles can be there, so you can refer to this graph at the left side. So this axis is the number of particles and this is the atmospheric altitude, this is the depth. You can see that from the initiation point, I mean where the interaction started or where the proton has entered the atmosphere, you can see that slowly the number is rising and then it is slowly then some of the particles will decay quite early. So slowly this number will be decreasing and at sea level you would expect a certain number of particles. Although it is not the maximum, it has a significant amount of particles. And particularly the particle muon. Muon is an electron-like particle but massive, of about 200 times massive than electron, but other features are very similar. They belong to the same leptonic family. The muons are also like minimum ionizing particles which can travel a very long distance without depositing much energy. So at sea level we have a large abundance of muons as well as electrons, positrons, and gamma. So you can see that some particles are created much later and they will be available in the sea level. So how we detect cosmic rays and cosmic air shower? So there are two prominent ways. Direct detection is when you place the detector quite up in the atmosphere or maybe just outside the atmosphere so that you can directly detect the cosmic primary, just the cosmic primary before the interaction happens. And the second method is that we can detect the secondary particles which are produced in an air shower. We can just choose have a chosen surface close to ground. So you can see that I mean these two methods has their own pros and cons. Direct detection will tell us very directly about the primary cosmic ray. However, it is not always possible to send detectors to very up in the altitude for a very long time. It is always convenient to have particularly large detectors at the ground level. But if we place the detectors at ground level, we won't be able to detect the primary cosmic ray. Instead, we have to detect the components of the extensive air shower which has reached that particular level. So the second method we call as the indirect detection of cosmic ray. And many experiments, they have arrays of detectors, suitable detectors. They have large arrays, detector stations, which are apart by a large distances. And I mean, many experiments employ that, and they have been measuring the extensive air shower and surface station of some scintillation counters, which will detect the gammas, charged particles, water Cherenkov detectors, mainly for charged particles, then fluorescence detectors, muon tracking detectors, and hadron calorimeter are different detectors which can detect different components of the extensive air showers. So the experiments can be like based on just a single detection technique. We can have experiments which have maybe the scintillation counter only to find out the gamma at the ground level, or maybe fluorescence detector to just find out the fluorescence component of the extensive air shower. But other, or it can be hybrid also. Hybrid means there will be two or more different type of detectors will be there. I mean, in the arrays, I mean, maybe some of the array would be scintillation counter. There can be some neon tracking stations in between, so that they can detect different parts of the extensive air shower at the same time, and we get more information on the particles. So examples of cosmic ray detectors are Pierre Auger Observatory in Argentina, Cascade Grande KIT. It's not, I mean, right now it's not taking data, but whatever data it has collected are still like it's open and we are still analyzing them. Magic has Cherenkov telescope array, it's upcoming. Then Ice Cube Neutrino Observatory, and there are many. So the interesting things about extensive air shower and primary cosmic rays, we can start by discussing about the flux, the number of cosmic primaries. Actually, there is a remarkable cosmic ray spectrum from 10 to the power 8 to 10 to the power 20 electron volt, and there are a power law dependence. In this plot, if you see here, the x-axis is thus the energy axis. It's in the log energy, logarithmic, and y-axis is the flux, number of particles. cosmic rays per meter square, per second, per solid angle, and per electron. You can see that it shows kind of a steep straight line. However, there are a few points at which the straight line changes its slope. So you can see a small kink here. We call it a knee around 10 to the power 15 electron volt. Then you can get a second knee, another kink at 10 to the power just below 10 to the power 18 electron volt. And there is an angle where you can just get a slightly opposing slope at close to 10 to the power 19 electron. We can detect cosmic rays up to 10 to the power 15 electron volt by balloon and satellite experiments by direct measurement. However, as the energy of the cosmic rays increases, our current detectors are not designed so that they can detect very high energetic the cosmic ray particles directly, because then what will happen that the particles will pass through the detector, deposit some energy but not entirely. So they will not be able to do a direct detection. That's why, starting from 10 to the power 14 electron volt and beyond, extensive air shower experiments are the handy way of finding out details about the primary cosmic. And there are certain puzzles. One I have mentioned here, that ultra high energy cosmic rays puzzle is about the source, that where exactly they are originating. At lower energies, most of the cosmic rays are coming from sun and then coming from our around our own galaxy. However, very high cosmic rays, which we call as ultra high cosmic rays, particularly say 10 to the power 17 electron volt and beyond, they cannot be confined by the galactic magnetic field. We expect that they may come from some extra galactic sources. So understanding and identifying source of cosmic rays is one of the very interesting challenges for uh, the cosmic ray physics. So what do we study in extensive air shower? Now instead of direct detection, let us just move to the indirect detection using extensive air showers. As you see that in extensive air showers, we are actually detecting the secondary particles at a certain level which is very close to the ground level. So basically, based from that, whatever particle we detect at the ground level, we have to reconstruct. We have to go to the other way to reconstruct the entire air shower, and we have to reconstruct the primary particle, what is the nature. So the reconstruction of the primary particle, the shower characteristics of the components are very important parameters aimed at by the extensive air shower object. So one of the open problem is identify correctly the primary particle of an ultra high energy air shower. So usually up to 10 to the power 15 electron volt. If we just see in this plot, up to 10 to the power 15 electron volt, most of the cosmic rays are protons. However, with increase in the primary energy, other nuclei to have significant share in the primary flux. So one important work, it's like many experiments, many reconstruction and simulation work are aiming at identifying the primary particle to know the percentage of at the abundance, that how many are some lighter nuclei, protons, and how many of them can be some heavier nuclei. If we have more information on the primary particle as well as about from the secondary particles, we can also map the particle interactions, because our, as I already said, that today's accelerators can go up to 10 to the power 15 or 16 electron volt very efficiently, but we don't exactly know how the particle interactions, what are the actual details of the particle interactions above that energy, because we don't have information. And although we have theoretical models, but in order to see whether those models are correct or not, we must compare them from some observations or experiments. And ultra high energy cosmic rays can be very, very useful, because if we can map about the secondary particles in the atmosphere, about the extensive air shower, it's actually like mapping the interaction. So in that way, we can study more about the interactions, the particular the QCD interactions at high energies. We can study those and compare the models. So this is one of the very interesting challenge, and it's ongoing. So now I come to I want to show you just one particular extensive air shower detector. It's a hybrid detector. I want to show you how exactly this work and how exactly this look like. As I said, I mean there can be some components. So let us look into the Pierre Auger Observatory. So just to check, am I still audible?
Yes, you are audible.
Okay, great. So Pierre Observatory is in Argentina. It's a hybrid detector, extensive air shower detector. It employs two independent methods to detect high energy cosmic rays. The first component is a surface detector, like array of surface detector, which like detects charged particles through their interaction with water. There are like more than 1500 stations, 1500 meter apart. The exact number is this. And the second component is fluorescence detector. It would observe UV light in Earth's atmosphere. So they also have 27 fluorescence telescopes. So let us look into how they look. So you can see that this top the images are the surface detector. They are basically tanks which would contain water, and then there are three photomultiplier detectors. You can see three bulbs here on the image which is at the right. These three bulbs are three photomultiplier tubes which would detect photon. So the principle of detection is Cherenkov, like detecting the Cherenkov radiation, that when charged particles enter in this water tank, like, but when a charged particle passes through say some dielectric medium at a speed higher than the speed of light in that medium, then this Cherenkov radiation, it's a conical radiation would be there. It's like a very equivalent of shock waves. So this Cherenkov radiation would be detected by these multipliers, photomultipliers, and in that way the radiation will be detected. So these are the stations which would detect the charged particles. And fluorescent detectors, because in extensive air showers, I mean some of the particles even at a higher altitude can interact with the nitrogen of air and produce fluorescence. It's a fluorescence light. In order to detect that they have 27 fluorescence telescopes placed at 4 different stations. It also has some multipliers as well as some mirror and some converging techniques, so that the light would fall on the photomultipliers and they can get detected. So you can see it's just a animated view that this all these dotted stations are the arrays, are the detector stations of Pierre Auger Observatory. And you can see that it's just an animated air shower where you can see these red ones are actually the charged particles falling on the detector stations. And these are the fluorescence light. These are actually produced a bit up, but then they can actually they can get collected by the telescopes. And in that way, extensive air showers are detected in Pierre Auger Observatory. And now they plan to have an extension where they will add stations to detect muons, because muons are very interesting particle. You have a large number of muons at the ground level, and they would they would contain interesting information to complete our understanding of the extensive air shower. And I also come to our uh, local observatory, which is the Grade 3. It's a TIFR lab station in it is situated in Ooty. So it's gamma ray astronomy at PeV energies. It's a phase 3, phase 1 and phase 2 are over. Now the third phase of this experiment is going. It has plastic scintillators. So you can see these stations. All these are plastic scintillators. They would detect the gamma rays, they would detect the light of extensive air showers. And in the middle, you can see some houses. These houses are actually like they house the muon detector. muon, some proportional counters which should detect muon and also find out the neon tracks. So it is also a hybrid detector. It actually now have the largest neon tracker in the world. And from that also we can have information on the gamma rays as well as the muons. And we can combine them to get a broader understanding. Okay, so that's all I wanted to give about the overview of cosmic rays and extensive air shower. Now I want to show you one example of just a token example of how to use this data to reconstruct or understand certain parameters of extensive air shower. So here I just want to show you one work of mine which is on the study of the muon component of extensive air shower and to see how would it improve our results. So the goal is to identify primary particle in every shower using muons. We would consider that it is a simulation study. We would consider that it's already detecting the gammas, photons, and apart from that there is also a possibility of detecting muons. We want to see how the detection of muon actually is improving or enhancing the reconstruction. So the information on the muons in a simulated extensive air shower was taken combined with these two information, the Xmax. Xmax is a parameter that is like the maximum depth, like a depth of in the atmosphere at which the number of particles are maximum. So it's a extensive air shower parameter. So basically at the point where the number of particles are maximum. So I can just go back here and tell you here. So you can see that the number of particles, they are maximum at some depth and then they again go down. So this depth at which the number of particles are maximum is we name it as X max, and it is one of the most very interesting parameter because it has a dependence with the the energy of the cosmic primary particle. So it can tell us about the cosmic primary particle. It also for different particles, like if I compare a proton cosmic ray and an iron cosmic ray, even if they are of the same energy, the depth will vary. So this will contain some information. So we take this parameter and then we just do a statistical analysis. And it was this was done to find whether we can design a new hybrid detector with some low cost large area arrays. So these are just some simulation details. We used Corsica, the package Corsica, to generate extensive air shower for with different primary cosmic primaries, say proton and iron. We took initially at different energies. We took a certain interaction model. We assumed that our detectors will be at 100 meter above sea level, and how the detectors will be oriented, like we thought of detectors of 2 meter by 2 meter sessions. We considered various scenario, very non-realistic scenario of having continuous detectors without any gap between them, which we can say as sessions apart by 0 meter. In that case, all of these dotted things, there won't be any gap between the detectors. However, realistic scenario is that you have to put detectors in arrays and at a distance apart, as we have seen in the case of Pierre, Auger, and Graves. So we considered a few different situations because our goal was to optimize the how much distance should be there between two successive detectors. It was like this study was based on some optimization for about the detector and the detector spacing. So basically to design a cosmic ray extensive air shower experiment in Israel. So it was just the initiating study. So what we can see here, I just simply tell you that suppose we take some primary cosmic primary at 10 to the power 16 electron. We just wanted to see that if the cosmic primary is different, will there be any difference in the secondary particle orientation at the ground level? So we have taken two cosmic ray primaries, one like proton and iron. And in this plot, you can see the red ones are like the red one represents information from the iron cosmic ray primary, and black ones from proton primary. And what we have done at the ground level, the detector level, we just try to see that how these secondary particles, muons, particularly the muon component of secondary particles, the number of muon differ as we go away from the core center of the extensive air shower, and also at different energies. So these are like some energy and radial beams, and you can see that some of the beams you can see a significant difference between proton and iron. It's just the number of muons. We observe a significant difference. We are plotting number of muons versus x-max. So this is giving us some difference, which indicates that this can be used as a differentiating parameter. So we wanted to take the number of muon and the radial shape of the muon component, how they are distributed horizontally at our detection level. We tried to map in the muon energy and the radial distance for each primary that we use. For this case, proton and iron. And we assume that the X-max is already measured externally, not from the muon detectors, but the scintillators or other detectors. The X-max for that particular extensive air shower is already measured. So we take that information and perform a likelihood analysis. So we actually map it like this. This rho ER square is the muon number density for a very small energy beam and at a certain radial distance beam. It's like a very small, thin band of radial band and at an energy. And we tried to parameterize them. We actually obtained a functional form like this, where there are like the C, R0, R1, D, and K are certain parameters. We tried to have this as formulation to have a functional dependence. And we see that it worked really well. Like we saw energy dependence on this. It gave quite stable fit results, and it made calculation efficient compared to the beam data. We just can use this information. So we constructed a likelihood function. Likelihood function is a statistical parameter which can actually give us a comparison between different models and data. So our likelihood function involves two components. The shape basically how the muons are distributed in a radial, like radially how muons are distributed. And ln stands for the number of muons. So we defined likelihood function for both of them, and we actually we define them, and just we have done a statistical analysis where we have one component that will determine the difference in shape between two different models, and the other part will determine the difference in the number. Now, if we project them, what we have found that if we take ideal muon detectors and there is no gap between the detectors, then for primaries of energy 10 to the power 16 electron volt, if we assume it's 100% collection, so no gap between the detectors, we can actually statistically differentiate between proton and iron primary. So basically, it gives an idea of differentiating the primary particle, basically finding out the type of the primary particle. Instead of this ideal non-realistic case, if we go to 1% collection, like after air shower, just 1% is collected, so the detectors are like 20 meter apart, then we get something like this. We still have, we can still differentiate, but now the differentiation is not so good. However, we have to live with that. We cannot have 100% collection because extensive air showers are very much broadened. We can then go to even more realistic case like detectors who are 50 meter apart and detectors are 200 meter apart, and we see that we still have the differentiation up to certain confidence. And this is from the muon part of the extensive air shower. So then we did it for different energies, and we see that as the energy of the primary is more, the differentiation power is more. One thing is that the cosmic ray flux actually decreases with as energy increases. So the number will be less at high energies, but the differentiation power is more. So the both of them can be complementary in finding out the cosmic primary. Then we did it for different detector resolution. So instead of ideal detector, we have a realistic detector where there will be certain width in the detection. So we do not detect the energy precisely, but within a band like that. We applied the detector characteristics and we check the differentiation power. So we also checked with hadronic models. Hadronic models are for interactions at high energies. So since there are different models, we know that we need to optimize the interaction, and for that cosmic rays are cosmic rays are very good tools, because already there are cosmic rays present at very high energies which are beyond today's accelerators. So cosmic ray information as much that we can grab from extensive air showers can be actually used and fitted to check these hadronic models and to correct the hadronic models for high energy interactions. So this is just a comparison between a few different hadronic model, and we see a difference. And this is a result where we actually, instead of just using proton and iron, we use three groups, like the lighter nuclei, intermediate nuclei, which is group 2, and heavier nuclei, group 3, based on the atomic number. And then we see how much the differentiating power at different confidence levels and at different energies, because this gave us a fair idea of the enhancement when we use the muon information. So actually then this also gives us about idea about upgrading existing surface arrays by introducing muon detectors. And for muon detection, arrays of large area, like some large detectors, low-cost detectors are quite suitable. You have to just put arrays. At each station, you have to put a few layers which can detect the muons quite easily. Reasonable options that we look for are like this is still ongoing, like gaseous large area detectors. And there are different, different detector technologies available, and maybe we need to upgrade them. So this is something which is ongoing. So to conclude this work, of course, cosmic rays are very interesting. I gave one overview of the cosmic ray and extensive air shower, the detection, just example of Pierre Auger Observatory. And since in extensive air shower there are different particles involved, a simultaneous measurement of different types of secondary particles, basically using a hybrid detector, is very, very important to understand extensive air showers. So the study that I have shown, from my research work, is including the muon component, and it shows significant improvement in the results. So muon itself can be used to distinguish between the cosmic primaries. So this can be a useful parameter. So in this way, and maybe including more and more information, the composition of the primary we can find, and actually that can be used to probe the source of the ultra high energy cosmic rays. Like if there are some heavier nuclei, and if we also have the direction information, we can focus in the sky and we can figure out what is the source and what kind of particles are coming from the source. And based on that, we can actually probe more. Also, coupled with the telescope or other astrophysical measurements, we can actually try to understand more about the astrophysical source. For example, the blazer, where we simultaneously detected the neutrino as well as the gamma, actually gave a very good beginning to understand the process of mechanism of the neutrino interaction of the particle neutrino in blazars. So it also initiated the validation of different models. So lastly, I just want to introduce my lab. My lab is like neutrino and astroparticle physics. It works on neutrino and astroparticle physics. So we call the lab in short as NEWAP. So right now we have five members except me, two PhD students. So basically, this extensive air showers and all are not exactly my primary research interest. I mainly work on neutrino phenomenology, non-standard effects, sterile neutrinos, then detector simulation and instrumentation, like for example for silicon PMT detectors, and then bits of simulation and reconstruction for extensive air showers. And recently, we are also working for development of deep learning algorithm, machine learning for deconstruction in high energy physics detectors. So how to use the data and how to efficiently reconstruct. So these are our research interests. And we are currently associated with three experiments. The hypercamioka neutrino experiment, it is situated in Japan. It's an upcoming experiment. Then grapes tree, I already talked about this. And I am an alumna of India-based Neutrino Observatory. I did my PhD in this and I still work for this. So if you have any further questions or anything about this, then actually you can just drop me an email. I'll be very happy to answer your queries. So that's all I wanted to say. Thank you for the kind attention.
Thank you very much, Moon, for the nice talk. Do you see
Thank you.
questions in the chat that you want to take up?
Okay, just maybe I just stop sharing for a while to see the screen. I mean, I also have a shared spreadsheet. Like if someone asks question, I will be getting this. I mean, is it for this talk or I mean, they can ask later also.
Okay, so far I don't see any questions on the sheet. Yeah.
Okay, but if somebody has any questions, they can just unmute and ask, I guess.
So there are no questions in the chat, is it?
Yeah, the chat, I don't
Sometimes.
see any questions.
Okay. So the last slide you showed the email address, but was that your email address where participants can contact you?
Yes, I can just share it again.
Yeah, because there have been some inquiries about possible internships and so on. So, yeah, if anyone wants to contact you, they can contact you via email.
Yeah, sure, I'll be very happy. And as I said, cosmic rays is not exactly my prime area of research. So if they are interested to know about anything else, I'll be very happy to answer.
Nice.
And the audience might be already very tired because it's almost the program is almost ending, right? They have attended many
True.
lectures.
Yeah, so it has been an intensive program. So 5 weeks is a long time, and also there have been lectures on many different topics. But this last week there have been research talks from you and from other speakers who are currently working on at like the edge of astrophysics, and so for the participants this was a good experience to know about what are the applications of the things that they are learning.
Right.
I'm sure they will take a little time to absorb all the information. So we will keep the website up, and so if you also share, you already shared the slides,
Yes,
so
yes.
we
I
can
have shared with you.
yes, so we can upload these, and I think the students can also or the participants can go through these to take a little more time to understand and connect things.
Okay.
But I think this is a good platform to know about also what is going on in the different labs and
Right.
So this was actually the last research talk and the last lecture of basically of this school. There is only one colloquium now from Professor Sri Anand, and that is the last event of this school.
Yeah, it's from 4, I suppose.
Yeah, it's from here. Okay, so if there are no talks, yeah, there are no. If there are no questions, then I think we can end the session here.
Okay, I would like to thank you once again for coordinating this so nicely and giving me the opportunity to speak.
Okay, so this is yeah, it's a pleasure from our end as well. Thank you for joining.
Yeah, thank you. I'll be in IUCAA in July, so hope to meet you in person soon.
I see. All right, that's good to know. Great. Okay, then we'll end the session here. Thank you very
Thank
much.
you.
Yeah, bye.